So first of all, let me thank for the organizers for this very nice organization, Rui, Joey, and Hoyos. It's a pleasure to be here and to discuss about these topics. Okay, so the idea of my lectures is to discuss some general properties of dynamics, and specifically in systems that has some quantum properties and also exploiting the many-body interactions on these systems. Okay. So I split the 5 lectures more or less along these topics here. So first, I'm just going to focus on what we call as closed many-body systems and talk about thermalization in the system. So essentially, it's a bit of what Victor has written here. That we had at the beginning some equilibration, and then you go out of equilibrium, and then you go for the thermalization. So it's funny because at the beginning it's more or less what Hoyos was presenting to us, and then you cover the second part, and I intend also to cover the third part here. And it was not planned, so that's why it was interesting. Okay, it was completely planned then. I'm sorry. Okay, so and then, yeah, for today I'm going to focus on this thermalization and the lack of thermalization in one specific class of dynamics. That is what we call many-body localization. And then for the next lectures, I'm going a bit outside of these closed many-body systems. I'm going for open system dynamics that has some resemblance to lack or thermalization dynamics. And then we are just focused on this specific class of open system dynamics that is given by Gorini, Kozakovsky, Sudarshani, Lindblad master equation that I don't know why, but we just call it by Lindbladen, but there are some other people that have derived this as well. And then for the third, fourth, and fifth lectures, I'm going to give some examples of how these open systems can be very interesting in what we call a synthetic open system dynamics that is not really naturally arising in your system, but we can engineer using some state-of-art platforms today. And specifically, we can see this, this novel phase that's boundary time crystals or dissipative state engineer with dark states with many-body topological properties and so on. And then some applications of how these non-equilibrium phases could be useful also for some quantum tasks, such as in quantum metrology or also in topological quantum computers. Okay. So for today, I'm going to also just be on slide-like presentation. I'm not going for the blackboard, but I promise that tomorrow I'm going to make more efforts and go completely on the blackboard and open the calculations. Okay. But if anybody has any questions or any doubts during the presentation, just let me know. I'll be happy to try to answer these questions. So I'm just going to give a brief introduction of what do we call as dynamics in many-body systems and some of its issues or some of the nice perspectives that we have today to study this type of quantum dynamics. What do we mean by thermalization properly, how we define this in unitary closed dynamics, and how we avoid this in some case as localizations. Okay, so we can go directly for this idea that in some sense, this field of studying the dynamics of quantum systems has already been an interesting subject, but recently, due to this dramatic experimental progress, it has been boosted somehow, or the interest of the community along these directions. And by the experimental progress, I mean these different platforms, for example, and also many others, that you can engineer very well your quantum system, put it in a non-equilibrium context that has a long coherence time, some many-body interactions as well, and you can tune very well these dynamics and also to exploit the observables of the system. So for example, in platforms such as ultra-cold atoms in optical lattice, you can get a bunch of atoms, and then you can cool down to very low temperatures in such a way that if you put 2 laser lights in the counterpropagating field here, they are going to generate a very small optical potential. And since these atoms, they are very low temperature with a very low kinetic energy, it's enough to trap them, and then you can see the dynamics of particles in an optical lattice in general that we study in Ising-like models or any type of lattice systems, right? And then you can also exploit, to engineer different type of interactions between these atoms. Depending on the atoms that you put here, they're going to have different ways of seeing each other. You can tune the strength of these lasers in such a way that you can also tune the depth of these optical potentials in a way that you are tuning how the atoms, they are going to hop between your geometries. You can also change the geometries with some certain precision. So you can play a lot with Hamiltonian engineering in this type of platforms. And not only in optical lattices, but also some other platforms as ion traps, where the idea is essentially the same, but now you have, instead of neutral atoms, you have ion atoms, and then you can trap them using some electrical fields in different directions in such a way that you can trap them, and they are going to have some Coulomb interactions among each other, and you can engineer different types of Hamiltonians as well. Okay, and let me see also there are nitrogen vacancy centers. That's quite interesting as well, and this is being built right now in CBPF in Rio de Janeiro. So there is a lot of perspectives to study this here close to us. Here you have, you do not trap the particles using cooling and using these electric or optical fields. What you do is that you build these crystal structures, and then these crystal structures, they have some defects. And if you look for these defects, the properties of these defects, they can be seen as essentially a two-level system, or something like a spin system. So you're going to have a lot of these defects in these diamonds. Each one is going to be an effective spin particle or spin subsystems, and they can also interact among each other. You can play with them. You can manipulate these defects as well. In other words, you're manipulating your effective spins in your state-of-art platform. Okay? So in summary, this recent progress allows us to understand or to realize quantum and many-body systems that are very well isolated from the environment. And when I say that they are very well isolated from the environment, it means that I have a long coherence time where the quantum properties are still present, and we can study how it behaves for these times. We can tune very well the interactions, the geometries, and this type of platforms. And also we can prepare some non-trivial states or highly energetic states to prove, for example, the thermalization of the system or the lack of thermalization possibility as well. Okay, so then many questions arise directly, right? So if we have these platforms, what are the possible types of dynamics that the system is going to be driven if we just relax them? We just leave it with the interactions and see what happens, right? Of course, I just already mentioned how the thermalization properly arises, but now you see that we have some kind of issue because it's a different type of thermalization that might occur in our system, because we don't have an external bath, right? Every time that we talk about statistical mechanics and thermalized system is because we have an external bath that we're exchanging information, exchanging particles, and then here is a completely different framework that we have a full unitary isolated from the environment. And of course, how can we fail this thermalization? And if so, if we fail thermalization, how these quantum effects appear in the system, how important they are. And this is, of course, very interesting because it means that we could try to explore these quantum effects in non-thermalized systems for quantum applications, as I mentioned at the beginning, for quantum computers that has a long coherence time, for metrology or any other things like this. Okay? So first, what do we mean by thermalization in these unitary systems? Okay, so in conventional statistical mechanics, when we say about a thermal state or a thermal equilibrium state, it means that we have a system that is in contact to a very large environment, a reservoir, in the sense that the reservoir is roughly unchanged by the system dynamics. And if we wait for a long enough time, the system is going to probe all of the possible microconfigurations here, and is going to be roughly described by a Gibbs ensemble, by a microcanonical ensemble. That's the framework that we have in classical statistical mechanics, right? But here we have a completely different situation. We don't have a system and we don't have a bath separately. We just have a full universe, let's call it this way, that is evolving according to our unitary dynamics, okay? There is no external reservoir, but we could still ask, or we could still argue, if the system could be a thermal reservoir for itself, okay? In the same sense of classical statistical mechanics. So now the system evolves according to the whole unitary, but what happens if you look just for a small part of my full system? Could it be that it resembles the classical case of a reservoir that is much larger, behaving as an environment to thermalize the small part of my subsystem? If so, then I would have some stationary observables or some stationary steady states for my local subsystems, and we could have some kind of quantum statistical mechanics description for my small subsystems. Okay? Okay, so what do I mean? So just consider a very simple case that we have a 1D spin chain, and we want to see a quantum quench dynamics in this 1D chain. Okay? So imagine that you have particles in this chain here. They can be either occupied or not occupied. And these particles then they can tunnel along this chain, and they can also interact with each other if they are close together. Okay? But imagine that this configuration here is not the ground state of your Hamiltonian. It's not an eigenstate of your Hamiltonian. So if you let it evolve, the particles are going to start to tunnel along the chain, also interact, and you're going to have, at the end of the day, if your system thermalizes, all of the particles, they might be completely homogeneous along the whole chain, right? So if we look for any subsystem of my full system, it's just going to be described by a canonical, like statistical mechanics. Okay? In other words, at sufficiently long times, all of my local observations of my full systems, they appear thermal, or in other words, it means that the information that was encoded in the initial state, it just spread along all of my chain, and then I cannot recover locally this information anymore. Okay? So, yeah. Perfectly. And that's what you mean by being internalized, this reduced decimation being described, yeah, it's exactly like this here, for example. Okay, so that's exactly the point. So you cannot look for the full system because it's always a pure state. It's always evolved by unitary dynamics, right? But we can still try to recover the idea of a thermal state by looking at some subsystems of it. So if I trace out all of the rest of my universe, I can ask if what left with me here, it behaves as a thermal state or not. Okay? I'm going to open these calculations soon also. So in fact, in this case, that is, let me say, 99% of the dynamics that we see on equilibrium many-body systems. It has this type of losing the initial information and going always to the same type of local observables, the same type of thermal state at long times. Okay? And in fact, not only the particles, if you look locally here, they're going to have this homogeneous or the lack of the initial information, but actually all of the local physical observables, you can compute then by just looking for an effective density matrix that is like a microcanonical density matrix. And when I say microcanonical density matrix, it means that it only depends on some extensive parameters of my subsystem. So I can fully describe all of my observables by just giving what's the temperature, the effective temperature of the subsystem, what's the effective energy, the chemical potential, and so on. Okay? But then, what if the system do not thermalize? So then, very simply, the information that was encoded initially in my system here, it's not completely lost during the dynamics. So for some reason, even if you wait for infinite long times, the system is not going to be homogeneously distributed along all of my chain, but you still have this type of memory of the initial state configuration. And if you look for a different initial state, it would lead to a different long time dynamics as well, okay? So you cannot always describe the long time by the same microcanonical density matrix. Okay, this is what we call by non-thermalized system, or in other words, ergodicity breaking systems, and it's going to be somehow the main focus here. Because in some sense, they allow us to construct some stable quantum phase of matter and some uniquely non-equilibrium features that are not present when your system is in equilibrium or thermalized. Okay. So there are many different, not many, I'm sorry, but there are different instances where this type of phenomenology occurs. Here we are going to focus on what is called Anderson localization and then generalization to the many-body setups, that is the many-body localization. But let me also say that in Floquet systems, just like the Victor was looking, you have also some examples that is called the time crystal phases. So if Victor is not going to present in the next lectures, I'm going to try also to cover here. And also, let me say there are some other types also of non-ergodicity breaking systems that are based on different mechanisms, many-body scar, Stark localization. This is a very interesting subject. I'm not going to cover, but if anyone is interested to discuss, just let me know. Okay, so let's thermalize or formalize mathematically this thermalization. So there is a very famous mechanism that try to explain why thermalization occurs or when thermalization occurs in my system. And it's called on this eigenstate thermalization hypothesis. So it's a very strong hypothesis that you do in your eigenstates or in your Hamiltonian, such that it guarantees or is sufficient condition for your system at long times to have a microcanonical description, okay? So first, let's see what does it mean as ergodicity in a quantum system. So we cannot just use the classical ideas and translate directly to the quantum. It's a bit problematic here. Because in classical systems, we say that a system has some ergodicity if when we look for a very long period of time, the average of our system, it's going to go through all of the microcanonical microstates that can be assessed within the conservation laws of my system, okay? So if I look, for example, for the phase space, particle position, and momentum, in ergodic systems, if we wait for a long enough time, it's going to cover all of my phase space with different probabilities, and I can construct a probability distribution that is my canonical probability distribution. But on the other side, if the system is non-ergodic classically, it means that it cannot access all of the possible phase space possibility, okay? But if we try to just use this type of definition and going direct to the quantum case, it's completely wrong. In the sense that when we have a quantum system, in our case, unitary dynamics lives in the Hilbert space, we cannot construct the completely direct analogous as a phase space, right? Because we have the observables do not commute, and we don't have the fully precision on different observables of my system by Eisenberg principle, okay? And in fact, this is what happens. So for example, consider that we have then our initial state. I just expand it in my eigenstates of my Hamiltonian. And here alpha is just the eigenstates of my Hamiltonian. And this is just the probability of my initial state in each one of them. And when we look for the dynamics of my full unitary system, it's just expanding this with the unitary Schrödinger dynamics. And this is just going to add these local phases that depends on the energy of each one of my eigenstates, okay? Apart from some weights, that is the probability for each one of my eigenstates. So then if we try to recover the idea of ergodicity here, we see that it's somehow not good, right? Because here, the probabilities of all of these different eigenstates here is set by the initial state. and it does not depend on the initial state, right? This phase here, when you look for the probability, is just is average out, okay? Then if you think that these are the possible phase space configurations of my spins, you are never changing the phase space configurations. It's always fixed there. So you cannot exploit all of the possibilities in my phase space. It's always constant because of my initial configuration, okay? And then, okay, it means that in some sense we need to modify our notion of ergodicity or thermalization when we are in this closed system dynamics. So how we do it? So we recall that we are always interested in looking for some local observables of my full systems and how it behaves when we wait for a long enough time, okay? So then we are interested in looking for infinite time average of a physical observable. If we look then for this type of observables, it's just taking the limit of a very large time and looking for the average of the expectation value of my unitary dynamics here, okay? Just see the time. Okay, and then just coming back to this expansion here, you see that when we make this expectation value, we are going to have two different terms in this integral here. The first term is when you have alpha on the left and alpha on the right, and then the local phase, they are going just to be out of these terms here, and this is what we call by diagonal terms. But also, when we look for the off-diagonal terms, they're going to be something like this. We have these coefficients alpha and beta that are determined by the initial state configuration, but then we have a non-trivial time dependence phase on the second term for my observables in here, okay? But then we assume here that you don't have a strong degeneracy in the spectral properties of your Hamiltonian. In a way that even though these energies here, they can be very close to each other or exponentially close, depending on the case, when you look for the infinite time of these quantities here, these quantum complex numbers here, they are going to still be non-negligible, and then they are just going to be average over all of my complex unitary plane, okay? And then when you make this integral here, they're just going to be vanishing or negligible, and you don't have any non-trivial dynamics or non-trivial contribution from the second term here. So in other words, we just recover this simplified version of my observables at long or infinite long lifetime. That is just the sum of the probabilities of my initial state in each one of my eigenstates with no time dependence anymore. And as expected, it depends on the initial configuration that we have there, right? You cannot go through all of the possible ergodic configurations. Okay, but then we make an important observation. That is, we're looking for the thermalization of physical states. It's not any initial state that I want to prepare, but what I call physical, in the sense that it's something that I can easily generate in my experimental platform, in a way that if I have a bunch of spins, I don't have much correlations between each one of my spins or each one of my subsystems. It's just that I can manipulate them locally, pointing to different directions, perhaps engineer some type of interactions between close or nearby spins. But this is a class of low entanglement or fast preparation states. And if you look for this class of what we call physical initial states, the probability along the energy spectrum of my Hamiltonian is not completely spread out over all of my spectrum, but actually it always appears somehow localized in a region of my spectrum, okay? Then the expectation values, it has somehow the simplification that we just need now to look for the sum over the spectrum around some average value of my full eigenstates Hamiltonian. Okay, and then it comes the important hypothesis that if we want that this expectation value here to be the same for any initial condition preparation of my system, all of these terms here, they need to be the same expectation value for all of the eigenstates. So in other words, all of these expectation values over alpha here, the eigenstates, they need to always to be the same number that depends essentially only on this average energy eigenvalue here, okay? And this is what we call as eigenstate thermalization hypothesis. So if you have this very strong hypothesis on your full spectral properties of the Hamiltonian, then for sure you're going to have that this does not depend on the initial preparation of your system. It's always thermalizing to the same, okay? Just to be more precise, what we call by this expectation value of a microcanonical ensemble is just assuming that the density matrix is just a flat distribution around your average state, and somehow it's exploiting all of the possible microcanonical configurations as we had in the ergodicity hypothesis in classical systems. Yep. No, it's somehow recovering the idea of the classical state, yeah. So recover somehow that if all of the eigenstates, when you look for the observable level, is not the density matrix level, it agrees with the expectation value of this effective microcanonical state. But this is different than say that if I trace out all of my external degrees of freedom, the reduced density matrix is going to be this guy here. Because this is just a statement about the expectation value of observables, okay? It's a bit tricky, but in essence, it tries to recover the idea of a microcanonical ensemble in classical systems as well, okay? So then the main assumptions here is that for physical states that we can prepare in the lab with no big efforts, and assuming that all of the eigenstates of my Hamiltonian, they agree with the expectation values of an effective microcanonical ensemble, then the observables do not depend on the initial preparation, or we have the thermalization appearing in the system, okay? So this is a very strong assumption in some sense, and the main, we can, of course, ask if this is really the case if you look for different systems. And indeed, it was tested in many different numerical simulations, let me say, in lattice systems such as in spin, bosons, or fermions. And at least at the moment, all of them has agree with this type of expectation that all of the eigenstates, they behave with this microcanonical ensemble. But it's still not clear if this is the only mechanism for the thermalization of any system. So this is for sure one sufficient condition in such a way that the observables, they are going to be thermal, but perhaps there are different ways to approach this question as well, okay? So now it comes some interesting consequences that are going to be important for the lack of thermalization. Yes, yeah. So this average energy here is, I'm sorry, it should be an alpha here for this average energy here. So it depends on your initial preparation that has some average energy around some region, yeah? But then, yes, given that you have just this average energy as your extensive parameter, you can describe by this corresponding canonical ensemble, okay? So for different initial states, perhaps you have different peaks at different regions here. But each one of them, you assume that it agrees with a corresponding microcanonical ensemble at that average energy as well. Okay. There are some further details. I'm not going to mathematical details, but it's also assuming that entropy here, I mean the off-diagonal elements, let me say, these off-diagonal elements here, they also depends on what's the size of, or the entropy of this canonical ensemble, just to say how these fluctuations are going to die in the thermodynamic limit or in the long time. But in essence, that's it. Okay, so now some important consequence of having eigenstate thermalization in a Hamiltonian. So in essence, it's saying that all of my eigenstates, they obey these strong hypothesis, or in other words, that they have thermal observables. So if I look locally, it behaves as a thermal ensemble, right? In other words, okay. If I look locally, I don't need the ETH, right? Yeah, but not always you exchange energy in a way that you're going to lose the initial memory. And that's the main thing. For example, in localization, right? If you look locally, your system is frozen in some sense, right? And you don't have that a micro-canonical state to describe your local properties anymore for any initial state. Yeah, that's true. That's true, yeah. So that's why perhaps, I mean, it was tested and you have an agreement to the moment in all of the different numerical systems. But I mean, I think that is reasonable to expect that this occurs indeed, but there is not a proof, let me say. Yeah, and I mean, I think that today also there is some interesting discussion about the calibration of these systems as well. That's not really determinalization. It's more if your fluctuations are going to survive or not, and then you go for these off-diagonal elements of your observables. And then it might depend also on the type of system that you are there. Even in thermalizing systems, you can have different types of fluctuations between your subsystem to the rest of your ensemble. I don't know if it was more or less that you were in question. Okay, okay, so then, okay, thank for the warning. So then if all of my eigenstates, they obey a thermal description, if I look locally, it means that the reduced density matrix are thermal ensembles or thermally described by a canonical ensemble. And this is what we expect, that the rest of the system is acting as a thermal bath for my subsystem description. But in other words, it means that the entropy of this subsystem here is extensive, right? Because it's a Gibbs-like ensemble. And if we put, what does it mean, extensive entropy, in the discussion of entanglement and correlations, it means that the entanglement between my subsystem to the rest of all of my degrees of freedom, it's now exactly the extensive entropy, and it scales as a volume law with the subsystem size, right? So we can make this direct assumption because now the full system is a unitary, is a pure state, right? I don't know if everybody knows well the definitions of entanglement or entanglement entropy, but essentially if you have a pure state and you have a bipartition of this pure state, the entropy of one bipartition is exactly how much entanglement you have of this part with the rest of your degrees of freedom, okay? So then it comes because we have a full unitary dynamics and we can associate or can interpret the extensive entropy of my subsystem to the total entanglement that is shared between it and the rest of my degrees of freedom, okay? And in other words, it means that if we start with an initial uncorrelated system or a physical that we call the system, it needs to grow a lot of entanglement between it and the rest of my degrees of freedom. So in some sense, in thermal system, the correlations must spread very fast in such a way that you can always reach more and more entanglement that depends on the size of my full subsystem, okay? Then we can see one example of how it happens. So the paradigmatic or the simplest case that we always look for the Ising-like model, where you have a spin chain, and these spins, they are interacting along some preferred direction, along the z direction, but we can also have some transverse field or some longitudinal field on this spin chain, okay? Then what happens if you look for this type of quench dynamics to see for determinalization or not? So we can prepare our initial state in a null state, for example, where you have up, down, up, down, up, down, up to the rest of your chain. And this is not an eigenstate of my Hamiltonian. This is clearly, actually, if you look for the expectation value of this initial state here on the Hamiltonian, is going to give you a very high average energy. So it means that you have some very high effective temperature if you wait for determinalization to occur. Also have support outside this, but it's always like a Gaussian support, more or less picked around a fixed region. Okay? Because this is somehow a physical state on what we are calling here. Okay? It needs to have some support because it's not an eigenstate of the Hamiltonian as well. But this support has also some specific properties.
So you're saying that easy did one of your initial features?
Yes, yeah, it goes into this direction, yeah. Okay. So then what happens? Initially, you don't have any correlations between these spins. But the dynamics, it makes growing the correlations because of the Ising-like interactions of your spins, right? And also it creates some superpositions, it creates some coherence along the x direction, and also some other effects as well. So initially you can just look for a single spin that's not correlated to the neighbors, but then as time goes, the interaction between the nearest ones starts to play some significant role, and then this two starts to entangle, and also the two to the left. If you wait for a longer time, then the third one is going to also be correlated to the second, that was correlated to the first, and then the correlations of this block here, it starts to grow and grow. The correlation of a subsystem by partition, it starts to grow with time, okay? And if you look for how the correlation grows in time for the different size of these blocks here, you see this fast spread or the ballistic growth of entanglement in my system, right? So what you're going to see here is in log-log scale. You see that the entanglement is always growing up to some saturation value, where the saturation value is just dependent on how many spins you are looking for this bipartition, okay? So let me say here, for example, the first line is just L equal 8. So you see that the correlation starts to grow for a big block because of this light cone spreading of my correlations. Till some point, this light cone reach the total size of my partition, that is equal 8. When it reach 8, it means that everybody is now completely correlated to the rest of the environment, or what is playing the role of the environment. And then you have the saturation, and the saturation, it depends on the size of my subsystem, okay? This is what we call as thermalization quench of entanglement, or ballistic growth of entanglement in thermalizing system, okay? Now, let's try to see some contrast to this type of dynamics, or specifically in systems that fails to be described by thermal ensembles. So, what are the possible routes of escaping thermalization? One possible route is looking for systems that do not transport energy or do not transport particles at some point, in such a way that your initial local information do not spread all over the chain, and you do not lose this type of information, okay? And in fact, even in the 50s, Anderson was somehow studying this type of transport or diffusion dynamics in disordered system, and this type of phenomenology was out there at long time ago, I would say. So if you go for the paper, for example, at that moment, I mean, let's say that the main focus was looking for the diffusion of transport in fermionic systems or in spin chains. And then you see that even here at the beginning of the paper by Anderson, he says that, okay, this is a model that you don't have spin diffusion is negligible. And perhaps second, as the second main result of this discussion here, and probably more important, as an example of a real physical system with an infinite number of degrees of freedom, a macroscopic system indeed, in the sense of thermal system that we're interested here, but is a system that has no obvious oversimplification. You cannot describe this as just some effective temperature or effect energy or just some microcanonical ensemble, in which the approach to equilibrium is simply impossible. So this type of failing thermalization was out there at the 50s by Anderson discussion. And the model is somehow very simple. The model, so here I'm looking for fermionic systems, what we call a 1D tie-binding fermions, that the fermions, they can hop between the different sites, but the potential of each one of the sites is completely disordered, okay? So this is also a symbol that you can somehow obtain quasi-analytical solutions, because is what we call a quadratic fermionic system. You can diagonalize it, and that's why in the 50s it was already possible to understand very precise the physics of the system. And I don't know, I mean, here also I'm using this second quantization formulas. Not sure if it's used for everybody, but it's just saying that you have some operators that either create a fermion in the ith site or in the ith potential, or you annihilate a particle in the ith potential. And then the Hamiltonian is just making these two terms here, where you count the number of fermions in each one of this potential, and this is the chemical potential for each one of my height potential. And this one just annihilate a particle from one potential and it creates in the nearest neighbor potential. So this one just describe the particles making the tunneling along my chain. Okay, we are not going to need to go beyond this on second quantization. And then if we take a classical perspective for this type of dynamics, we can try to understand what are the possible scenarios here. So if J here, that is the kinetic energy of the particles along my chain, is not higher than the corresponding potential, then the particle cannot hop or cannot go to left or right because it does not have enough energy to go along this potential energy, okay? And then the system can be called somehow as a localized or very weak localized at some specific potential here. If you have enough energy, then the particles can fluctuate. But of course, a different question is how the particle is going to fluctuate, because all of the potentials, they are disordered as well. Each one has a different probability, okay? But now if we go to quantum mechanics, the situation is completely different. Because quantum mechanics says that the particles can also be interpreted as waves, right? We have wave and particle description. And in some sense, the particle can then have some interference in these hoppings that it behaves, that it makes along the chain, okay? So now we have the particles, even though it may not have enough energy to make the hopping or to jump between two neighbor sites, it can still always tunnel between these two sites because it's a wave propagating, okay? And also, it can not only tunnel, but it can also be reflected by each one of these disordered potentials, okay? So we can see more or less as the particle or the wave packet that describe the particle, if I put it in one of these optical sites, as it's going to start to spread and then it's going to be transmitted to the right one, but part of it is going to be reflected as well. And then it's going to arrive to the next optical lattice, and then part of it is going to be transmitted again, and part of it is going to be reflected. And this type of wave packet dynamics is going to occur many, many times. But then we notice that since this potential is disordered, the rate of transmitted and the rate of reflected of my wave packet is going to be disordered as well. And if we look for the average of the particle transmitted and reflected in each one of the sites here, you have some completely off-resonant interference of the particle with itself. And then essentially, if you look for the probability of finding the particle in each one of these far site position, is going to be very small or essentially negligible for my system, okay? And this, let me say, this is very different from the classical case. But in the classical case, the localization arises because of non-wave or non-interference effect. It's very different, okay? So on more formal grounds, if we want to look how these things appears mathematically, and this perhaps also go as one good exercise to do in your computer or even analytical in some case. We try to look for how is the wave functions or the eigenstates of these specific Hamiltonians or disordered Hamiltonians here. So in order to look for the eigenstates, we just look for these ansatz here. So we suppose that the eigenstate of my Hamiltonian is just this superposition of a probability of my fermion to be at the J site times the creation of the fermion at this J site, acting in the vacuum or in the no occupation of any particle at that site, okay? And then solving the Schroeder equation is essentially solving the H psi is equal to E psi for this ansatz wave function that I'm supposing here, okay? And this is not very hard to do. I mean, you see that one term here is just counting the probability of the particle to be at the jth site. So then we just have the Hj here applying to the probability of the jth site. And the second term here, you just look for the probability of the right neighbor and the left neighbor of each one of my sites. And then this is just j applying to the probability of j minus 1 plus the probability of j plus 1. And then in order to satisfy the Schroeder equation, I just need that all of these here needs to be, apart from an energy constant, the same probability of my ansatz initial here. And these need to be satisfied, of course, for all of my j's, right, in order to be a solution of my Schrödinger equation. So in order to solve this in the simpler form, we can just write down the set of equalities here in a matrix form. So now we have a vector, that is the vector of the probability of the particle in the first, second, up to the size of my chain. And I can translate this equality here in this matrix form, okay, where the H is just connecting to the diagonal elements, and the J is just related to the hopping of nearby fermionic sites, okay? So in the simpler case, and perhaps this is the case that you have already seen in many different instances, is when you have no disorder. If you have no disorder, you have that the diagonal part here is just equal 0, and then you just have the hopping of the particles. It's a very simple matrix to diagonalize, and this is just the block states, right? You're going to see that the solution or the probability of my fermions to be at any site, J, it depends on these complex phases where K is somehow the momentum of your particles. But in some sense, you see that the probability to be all along all of my sites is non-zero, apart from a phase that is the momentum phase. But now, if you add some small disorder to these diagonal terms here, so it can be completely random in the diagonal of the matrix here, you're going to see, and here I'm just putting the final result. You can also check numerically, I would say, it's easier. That the eigenstates now, they are not completely spreading over all of my chain, but they come as some exponential with some localized around the jth, around the C points of my chain, okay? And this is what we somehow expected, right? Now the particle is interfering with itself, and it cannot spread so far from the initial position that you put this particle, okay? So just some numerical results here, just to illustrate this. So here's the probability of the particle to be at the jth site, and in a chain of 5,000 sites. You see that if the disorder is very, very weak, there is the blue probability distribution here, that the particle is not completely delocalized on all of your chain, but is somehow spread over the chain, but still localized around some region. This is one of the eigenstates of my Hamiltonian. If I increase the disorder of my system, you see that the particle becomes more localized around the regions. If you keep increasing, the localization becomes stronger and stronger, and you have a very short correlation length of your initial fermion. Okay? So in some sense, if we look for the dynamics, it's going to be completely frozen because all of my spectrum is localized, and for any initial configuration is going to have some overlap into this type of eigenstates. Each one of the eigenstates is localized around some region, and then your full initial state is also going to be localized around the corresponding regions. So then we fail completely to thermalize, and this was indeed observed in many different platforms, let me say, but let me just mention this one in 2008, where you use these Bose-Einstein condensates in a one-dimensional trap, where you can cool down this ensemble of atoms in a very specific region here, very localized region. And on top of this, you can also create some disordered potential for the dynamics of my ensemble. So even though there's a lot of atoms here, it's still a very low density in a way that we can somehow approximate as a non-interacting system or an Anderson-like system. And then what you do is just you create this initial state around this position, and then you let it evolve with this disordered potential. And you see that even at long times, the system is still roughly localized along the initial position of your configuration, okay? So you see here in the log scale, for example, you see this exponential localization of the system, even for long times. The light red one is the initial one, and the dark red one is for a long time in the dynamics. It's still along there, okay? Okay, so this is Anderson localization that in some sense says that in disordered systems, because of interference effects, we don't have transport of energy, charge, the system is roughly frozen. But of course that in more realistic cases, we always have some type of interactions between these particles, right? We have phonons acting in the lattice. We have the particles can somehow see together and have some Coulomb interactions as well. So in realistic case, we have interactions that we need to take in account. And for a long time, it was a question if this type of phenomenology here, or this type of localization, would still be there if we take in account the interactions, okay? Yeah.
In the model, the disorder is on page, right? Not on chain. If I change this, looks like a uniform page, but the chain is now random.
Yeah, you also get the localization, yeah. Because now you are explicitly saying that the hopping between the particles in the chain, they are disordered, or the rate of the wave packet propagation is disordered as well. And depends on the site, right? And then if you look for a long distance from the initial configuration, the interference there is going to be completely random as well, the effective interference, and you are going to be negligible probability for the particle to reach there, okay? In fact, in Floquet systems, you can also see this localization, and there is very important to be in the hopping term and not in the magnetic field. Okay, depending on the Floquet system, of course, right? Especially in time crystals, because in time crystals, what you do some specific driving of your spins that, on average, it averages out this contribution of your disorder. But then you need to have some disorder on different terms. And for example, you can put the disorder here that on average is not going to be destroyed. I'm going to discuss perhaps in the next lecture more details about this, okay? Okay, so then the question was for a long time. Okay, I still have half an hour, I think, right? Yeah. Good. It's going to be important. So if this type of phenomenology, they survives for interacting systems. So for example, you can think of the same Anderson model with the hopping and the potential, but now you take into account that when the particles, they are very close together, nearest neighbor, they can also interact among each other, okay? And let me say that, I mean, the same model can be translated to spin models as well. Or the same idea here is a system that now instead of fermions that are making the hopping in our chain, is just a chain of spins that are localized. They do not move in our system. But now the role of the particle propagation in your fermionic chain is going to be described by exchanging spin of your spin chain, okay? So in somehow you use this Jordan-Wigner transformation, that's the mathematical transformation at the level of mapping fermions to spins or spins to fermions, and all of these dynamics here, all of this Hamiltonian, is just going to be mapped to a similar Heisenberg chain, okay? So I'm not going to the mathematical details, but it's essentially you assume that no particle is just spin down, for example, and one particle is having spin up in your chain. So the particle making a hopping is just then you flipping these two spins here. So the spin up that was a particle goes down, and then it becomes the vacuum, and the spin down goes up, and then it becomes the particle that did the hopping, okay? And this is just the first term here. While the interactions or the disordered potential is just the number of particles, or is just the magnetization of your local properties here. Not going to be very important how we do these mathematical formulas, but just to say that it's equivalent to look at these different models here. And indeed, looking for numerical dynamics in this type of systems. And here we are always constrained to short systems, right? 10 or 20, not much more than these sizes. People observe that even when you increase a bit the interactions in your Anderson model, the phenomenology of localization or of non-thermalization still survives up to some critical value. So this gives a strong indication that this model localization is really stable against these small quantum fluctuations in the part of interactions among them. Okay? So for example, there is this nice experiment here using those ultra-cold atoms in optical lattice, where you can create just this single one-dimensional optical lattice, and you can load your fermions in the even sites with no fermions in the odd sites. And then if you look for, again, if you look for this initial state here, for this model that they implemented, actually the expectation value or the energy of this state here is equal to 0. So it's going to be exactly at the middle of my spectrum, or in some sense, it's very far from the ground state, or very far from the maximally, the inverse of the ground state, right? It's not the maximal entanglement. But essentially, it means that the effective temperature in the thermal state of this state here is at infinite temperature. It's just the identity matrix along everywhere there, okay? And then they look for how much of this initial information of the loading of the particles in the chain is affected because of the dynamics of my system. And then is essentially that model. So the fermions can make the hopping, and if they are close together, they see each other and they interact among each other. Okay? And what they observe is very, I mean, they somehow corroborating this numerical expectation that if you don't have any disorder, so delta here is the disorder, you see that initially you have a very high imbalance, meaning that the particles are only at the even sites, but then very fast the imbalance goes to 0, and it means that the particles, they are equally populated in the even and odd lattice. As you increase the disorder, you see that you lose somehow some part of the initial information of your system, but then it goes to this plateau, and it means that it's not thermalizing after this. Okay? So in some sense, you have that the spins, they are not hopping anymore in my chain, or I have a frozen spin transport in my chain. But what it's interesting to notice is what about the correlations of these spins, right? What I'm saying here is that the particles, they do not make the flips anymore, or the spins, or the fermions, they do not walk in my chain anymore. But even though they have some microscopic internal dynamics, each one of my fermions or each one of my spins, they might be processing. And each one of them can be processing at a different frequency as well, okay? And this precession can be correlated because of the interactions that we are now taking in account between these fermions. So what happens that if you look for how the correlations are spreading in this type of systems? So we have that same mechanism, right, that initially there is no interaction between one spins, and then with time it becomes correlated with the nearest neighbors. And if you look for the entanglement entropy, the same entanglement entropy that we looked for the thermal state, you see that if Jz, that is the interaction, is equal to 0, initially you have some growth of entanglement. It's just the relaxation, initial relaxation of my fermions. And then it reaches this plateau here and it stays in the plateau forever. So in this plateau here is the Anderson localization, where you have no transport of energy. And also, because you have no interactions, you have no transport anymore of correlations or of information. But now, if you add even some small amount of interaction between your system, in this region here, where you have no transport of particles of charge, you see that at some moment, the interaction starts to have some dominant effect in the microscopic motion of these spins. And then you see that the entanglement starts growing, and it keeps growing up to a saturation of a volume law also, okay? So very different from Anderson localization, or where everything is completely frozen. Here, your particles are frozen, your fermions are frozen, but not the exchange of information that is occurring microscopically between them, okay? And this is a very interesting characteristic trait of MBL phenomenology. So here, you have the spreading of correlations, even though it occurs in a much slower form. It's not a ballistic growth of correlations, it's actually a log-like growth of correlations. And then you see that if it's going to saturate at some point at a value that depends on the volume of my subsystem, then the time to reach this value is going to be exponentially large with the number of spins, okay? And essentially, if you have just a short or a small quantum system that is a many-body localized phase, essentially you don't see this lifetime of it, right? Because it's exponentially large. It can be much larger than any lab parameter for our case. So in some sense, we can exploit this phase or this non-equilibrium phase, not only because it retains the initial memory of my system, but also because you have some growth of correlations in a controlled form. No, you don't have, I mean, if you look for, this is also one difference of MBL to thermal ETH states. Because in ETH, all of your eigenstates, they are thermal. It means that all of your eigenstates, they have a volume law entanglement, okay? But now in MBL, if you look for all of eigenstates, they have area law entanglement. But if you look for a long enough time in the quench dynamics, they are going to be a volume law, the dynamical properties, not the eigenstate properties of your system, okay? And this is also very important. And this is what causes this slow growth of correlations in my spin chain. Okay, so I mean, and this, I mean, is essentially some very nice features of localization in interacting systems, that absence of transport, slow growth of entanglement, logarithmic growth, or exponential long lifetime. But while to look for the magnetization properties or local properties of my system is very simple in these experimental platforms, to look for entanglement of bipartitions, of a bunch of spins, it's really a challenge there. So for example, you should look for the reduced state of a microscopic bipartition, right? So you need to make somehow the tomography of all of the degrees of freedom of your bipartition, and this is a huge task. So people are thinking on different forms to make it, like for example, looking for Fisher information, entanglement witness, and so on. And I just want to point one interesting approach here, or alternative approach to try to look experimentally the entanglement growth here, that is looking for what we call as monogamy of entanglement. That is a very unique property of correlations in quantum systems, okay? And the idea here is that by looking at just local observables or local correlation spreading, we can try to infer about the bipartite entanglement or the global correlation properties of my system. Okay, so what do we mean by monogamy of entanglement? So imagine that we have 3 particles or 3 spins, and we can compute the entanglement between each one of these pairs or each one of bipartitions of my 3 parties by this quantity that is called the concurrence, or is just another quantifier of entanglement between 2 parties, okay? And this concurrence, it's 0 if you don't have any entanglement between I and J part. And if you are maximally entanglement between these 2 parts, is always equal to 1. It has this maximum bound of 1. So what is the monogamy inequality? So you can play with this quantifier here, and you can always show that the total entanglement of A with B plus the total entanglement of A and C is always bounded by the total entanglement of A and the rest B and C, okay? Why this is called the monogamy of entanglement? Because it means that if A is maximally correlated to the rest B and C, it means that this is equal 1 here, right? But if this is equal 1, it cannot be the case that both of these guys here, they are also equal 1, okay? So if A is maximally entangled with B and C, either it is maximally entangled with B only and not entangled at all with C, or it is maximally entangled with C, and then we have 1 here, and not entangled at all with B, okay? It needs to choose with which party it wants to be correlated, okay? In some sense, we have 3 parties, and if 2 of them, they are correlated or have this type of correlation properties, the rest should be left outside of this thing, okay? And this is a purely quantum feature. This cannot occur in classical system. This is really some characteristic trait of entanglement. Because think in the situation where these parties, they could be classical, not quantum. And then think of the situation that A and B, they can be maximally correlated between each other, okay? So if you have this situation here, you can always look for the properties of B and clone the subsystem B, right? In classical system, you can always read all of the information and make a clone of this or a copy of this subsystem. This cannot be done in quantum system because otherwise we kill all of the probabilistic nature of my system, right? And then if we have the situation, I can clone the subsystem or make a copy of B, a B prime, that is essentially a copy that is always going to be maximally correlated to my initial one because it's exactly the same information that is put there. So classically, you can always have one party that is maximally correlated to how many you want, but quantum, you always need to choose which one you want to be correlated, okay? I'm sorry? So these correlations here, the concurrence, they look only for the quantum properties there. There's very few quantifiers that are able to look for the quantum correlations only, and concurrence is one of them, okay? But here you can think of any classical correlations, more general type as well, okay? So for example here, if this quantity here is different from 0, it means that the type of correlation that you have there is purely quantum. Okay, if you have just classical, it does not care. Okay. Yes, yes, yes. So if you set who is correlated, then you set the correlations for all of the other possible perpartitions as well. Yeah. Yes? So you cannot use the entanglement entropy here because of the following reason. So if you have that the full state is a pure state, and then you're asking what's the correlation only of A and B here, you need to trace out the C part, right? When you trace out the C part, the reduced density matrix of A and B is a mixed state. And the entanglement entropy is a good quantifier only for pure states, okay? It's a bit tricky. And that's why I use concurrence here, and this is Wutter's concurrence that is called, that perhaps I think is the only one quantifier that can really quantify the full entanglement of general mixed states as well, okay? I'm sorry, a bit. Yes, yes, yes. No, I'm sorry, I mean, for the entanglement entropy, Yeah, but if you look for the entropy of A and B here, it does not have the interpretation of entanglement anymore. Okay? So consider the case, for example, where you have some small correlations with C as well. Then when you trace out the C part, what is left is not a pure state. And then if you look, if you use the entanglement entropy for these guys here, you are using entanglement entropy for a non-pure state. And this is not defined as an interpretation of entanglement between them. Okay? You can always obtain this type of inequalities for quantities of correlations as well, like Discord-like correlations, but it's always also a bit tricky how to define these things. Okay, so how can we use this information or these properties of correlations in our many-body systems? So again, we recall the light cone, right? Initially, the systems is uncorrelated among the neighbors. And closed spins, they get correlated or they get entanglement between each other. And then as times go on and go on, more distant spins starts to be correlated among each other. And then what we know is that the global entanglement of these blocks here with the rest starts to grow, right? So in some sense, when the dynamics is going in my spins, I'm creating some global correlations between all of my spins. But what we know is that we cannot create global entanglement if my single spin is maximally entangled to all of the rest of my spins, because it's monogamous. He cannot do it, okay? So in some sense, to allow these global correlations of my spins, I need to be disentangled of pairs because of monogamy. So it means that while the global entanglement grows, my local pairwise correlations, it needs to decrease to open space for the global properties of my system. So in some sense, if I look for how the local pairwise entanglement dynamics is behaving, I have some indirect probing of the global entanglement properties of my full system, okay? So here is, for example, just one numerics of that model that was shown. So here is looking for the imbalance. You see that it has this small relaxation, and then it goes to this plateau. There is no transport of spins, no transport of particles anymore after these times here. But if you look for the average entanglement of pair spins, you see that it always keeps decaying for longer and longer times. So it means that the pairwise is losing correlations because of monogamy in order to allow the global wise to grow the amount of correlations. Okay? So this is somehow interesting because it could be easier to implement experimentally. Okay. Okay, and then just one last feature of, yeah. If you wait for a long enough time, the single spin is going to be every time less entanglement with the pair of it, yes, with the rest. Yeah. But if you look for the global one, now you have a lot of correlations between this global one. But if you look just for pairs, they need to decrease the type of correlation between them. Okay. In essence, you cannot be globally correlated and locally correlated at the same time. Okay. The pairs need to decrease in order to the global to open space. And this quantity, I mean, if you have more and more spins, then this is going to be more and more abrupt or more dominant, because then you have more and more global entanglement, and you decrease more the pairwise type of entanglement between them. Okay, and then just one last feature of this MBL phenomenology that, I mean, it's expected, or there are some claims, in some cases also some demonstrations in simpler case, that if you have this MBL-like dynamics, then you can map all of your Hamiltonian to some effective phenomenological model that is much simpler to see the physics there as well. It's not clear how to make this mapping in practice, how to make the calculations, but we expect somehow of this effective system to appear, in the sense that it's just described, but I'll say more details by these local bit excitations or localized excitations in my system. So let's just go back to the simpler Heisenberg model, where you have this, the hopping, right? Just the spin exchange, the disorder, local disorder, and the interacting term. So if we have a different perspective or a different interpretation of what is happening in this model, the simplest case is when we don't have hopping, no J, and no interaction, right? You just have this spin chain that is disordered locally with the potential. And then you see that all of the eigenstates of this Hamiltonian, they are going to be completely described by these excitations at each one of my site, right? Either the spin at ith site is up or down is going to describe all of my possible eigenstates of the Hamiltonian. And all of these operators here, they are somehow conserved during dynamics because they commute with my Hamiltonian, okay? When we moved to the non-interacting case, the Anderson localization case, now we have the hopping of my system. What we observe is that we still have some simple eigenstates for my Hamiltonian, but now instead of my eigenstates are completely localized at a single site, they have some exponential localization at some specific sites of my system, okay? So in this notation, it means that now I have some particle excitations or spin excitations that are going to be given by manipulations of my local spin, as long as these manipulations, they are exponentially localized at a fixed region. So these were essentially the wave functions of Anderson localization that I showed in the numerical analysis, right? And then the assumption here is that now if we add the interactions of my spins, is essentially that I have some new localized excitations that not only it can manipulate my spins at each one of my site exponentially around some fixed region, but also it can induce some correlated manipulations of my spins as long as it is also exponentially localized at a fixed region, okay? So in some case, in one case, the simpler case, we have excitations or quasi-particles that are just some single spin observables or one-body operators. And in the interacting case, these quasi-particles or these excitations, they can also be related to interacting spin operators, okay? If this is true, it means that my local Hamiltonian can be written in this weird basis or in this very specific basis. And then the Hamiltonian is going to be completely integrable in this basis. So it's going to have some local potential for these localized excitations, some interactions between the localized excitations, some 3-body interactions, 4-body interactions, as long as these interactions, they are always exponentially localized with the distance of these guys, okay? So it's a very weird, at first instance, Hamiltonian, but indeed, the phenomenology of this model here, it describes all of these main features of the MBL. The slow growth of correlations, the absence of transport, and the local monogamy property, and so on, okay? So we see that if this is true, all of these operators, they commute automatically with my Hamiltonian. So they are going to be some conserved quantities of my dynamics. And this is the absence of transport, because all of these excitations, they are not moving, they are not traveling in my chain. Even though all of these localized excitations, they can have still the microscopic precessions because of the interactions with the nearest neighbors or the next nearest neighbors and so on. So each one of them are going to feel some type of effective magnetic field and be driven with a different frequency in the precession. So you see that the precession do not change the Z magnetization, it's just around the X and Y, but then it can be related to how the others are also behaving. And this is what we call as dynamics induced by dephasing. So they are not flipping along the Z magnetization, but they can be out of phase in the frequency of each one of my spins. And this out of phasing microscopic dynamics can create entanglement as well. And this somehow explains why we have the frozen magnetization, but we still can have a slow growth of correlations between my L-bit excitations. Okay? Okay, this is just a simple example, but I may skip. But I just suggest then, I mean, as a good exercise, try to do these dynamics here for just two spin particles or just two L-bit operators. That is simply solving the Schrödinger equations for different initial configurations of my L-bit, right? So here is just, for this type of Hamiltonian, up is going to have a plus energy, and down as well. And if up and down or down up are the configurations, you have a minus J12. And then you can use any type of entanglement quantifier to see how the entanglement dynamics behave here. And you see that it grows up to some maximal value as well. Okay. Okay, so given that, I think that I can reach to my conclusions that essentially what I try to review here, or to give at least the conceptual ideas, is what do we mean by thermalization and some case where we don't have the thermalizations, as for example in disordered systems. And some of these main features of the specifically MBL dynamics, such as the lack of transport, you have some memory of the initial condition, this low correlation spreading, and this interesting perspective of looking for L-bit phenomenology. Okay, so let me just put some open issues along this discussion. Is that one of them is, I already mentioned before, that we assume that ETH is a reasonable statement or a reasonable expectation for thermalization to occur, but is it always necessary? There may be some case where not. This is an open question, I would say. And also, is there some other forms of localization that do not requires the disorder potential, for example? In disorder potential, it's very simple to see this interference of the wave function, but there are some discussion of disorder-free cases where you can also see this lack of thermalization, as for example in scars that I mentioned, and also looking for this type of phenomenology in Floquet dynamics is something very fruitful as well. Okay, so given that, thank you for attention. If you're interested in more details about these things or discuss something related, I'm very happy to do as well. Okay. If anybody has any questions, yeah. I'm sorry? Yeah, so what you assume in your physical system, okay, is that instead of having some localized non-interacting excitations, you have now interacting excitations. And these interacting excitations, they can come from different forms as well. Not only two-body interactions here, but also you have some three-body, four-body, and so on, okay? Yes and no. You have some long range because two spins can have some interactions, but the strength of these interactions, it's always exponentially small with the maximum distance between them. So for example, if you have these three here, I, J, and K, and J is in between I and K, the strength of these interactions is always related to the maximum separation of your spins, I and K, for example, okay? So you have long-range kind of interactions, but the effects of these interactions is going only to appear at times that are exponentially large with this distant separation here. And that's, I'm sorry? And eta is some effective localization of your wave function here, for example. So for example, for non-interacting Anderson excitation, eta is just how much this wave function is localized along the ith side. So it gives you the rate of localization, and here is the same as well. It's more complex because you have many different terms here, but it gives this idea of how much this exponentially is around the ith side of your chain. Okay. So if you put this CJ, in principle, no. Here you always have this type of phenomenology. So it's not for specifically, in principle, you can put any type of perturbation to this Hamiltonian here, that if this disorder is strong enough, you would still have this type of quasi-particle excitations there. So it could be even with some transverse magnetic field in the Ising case, it's still there. Okay. Of course, that is going to decrease a bit the localization, or in some sense to increase the eta exponent here. So, I'm sorry, decrease the eta exponent, but you could still have the lack of thermalization there. Okay. Yeah. So, yeah. Yeah, I would say that if you're close to the criticality, you could still employ ETH, in the sense that if you're close to criticality, you are close to have a degeneracy, right? But you don't have the full degeneracy yet. I mean, you could argue or more or less in this sense. And in this case, when you make the infinite time average, and this is a very strong assumption, even some epsilon of no degeneracy will have some average alpha in your full dynamics, okay? Exactly. This is a very important thing, yeah. I mean, the non-commutation of the limit of time and the number of degrees of freedom of your system. And this is the same also for symmetry breaking states, or because they do not commute. You first need to make the infinite time. The infinite n, and see that these configurations are stable or not. Here we are doing the opposite. We make the infinite time, and then we see how it behaves for finite systems. Okay. Yeah, this is a good question. I mean, and somehow an open question as well, because if you go, I mean, there are some works that go for the very deep localization regime of the Heisenberg model, for example, and then you can try to obtain this L operator using some perturbation theory, for example. So you say that omega here is much larger than J and Jz, and you know what are the eigenstates of this only part here is just this product state. And you try to obtain the new eigenstates by just perturbing in first order or second order this type of eigenstates here. Then you can somehow obtain some quasi-localized eigenstates here. So I know that there's some discussion, even in this case, of perturbative arguments. And for the general case, no, it's an open question. So how to obtain? So that's why I'm saying that this is a phenomenology model that makes sense if you try to reason the physics behind. And if you look for the dynamics, the numerical dynamics in this phenomenological model, it agrees with the physical model as well, but it's not so easy to make the full mapping of these localized excitations. At least I don't know of any work that obtained these guys analytically. Okay. Yeah. Yeah. So if you do not access all of the micro states of your system, then it means that you're not going to thermalize, for example, okay? And if you do not thermalize, it means that the system keeps some initial memory of how it was prepared, okay? And this is essentially what happens in this case here of a disorder system. So let me go, for example, in this case here, for example, right? So we start initializing the system with a very specific information that they're populated only at even sites. And you see that with disorder, instead of going to 0 in the imbalance here, where all of the sites, they are equally populated, now some of them, they are not so equally populated anymore. So it means that it somehow remembers that you had this initial imbalance on your configuration, okay? And this occurs because of disorder. I don't know if it was your question, but yes, it can happen. Which phase? I'm sorry? Ah, okay. Yeah, then, yeah, but then I think that the discussion of strange metals is more on the classical localization, but yeah, I don't know much. I know very superficial about these things. Perhaps Hoyos or Victor know better these things, but I don't know. Okay. Okay. Okay, it's answered then. Yeah, no, yeah, there are some controversies, especially because you see that the lifetime for these phases here. Oh, I'm sorry. Okay, so you see that the lifetime of these type of frozen dynamics, it's really big, right? If you have just, let me say, 10 spins, it's going to be more than what your computer can go with the numerical precision, for example. And then some of the questions is, or some of the controversies, is that if you keep increasing the number of particles in your system, this is always going to behave as this is scaling with n, or does it mean that at some very long time, but still finite time, it's going to start losing these localization properties? And this is a question that at least numerically we cannot address, and also to solve these things analytically is even hard. But there is these arguments that perhaps some parts of my spin chain, they are not completely localized, they are somehow thermal, and this thermal behavior could be spreading, or these thermal islands in my chain could be spreading and destroying the rest of the localization of my full chain. But to observe if this really happens or not, I mean, either you need to solve analytically or to have some better idea than just looking for the numerical dynamics of these guys here. Okay. But yeah, but there are a lot of controversies. So let me say that from the practical point of view, this is okay, because we don't care if this is going to be infinite or not. We just care if this is long enough for us to make what we want to do in the lab that are good quantum mechanical properties. But from a fundamental theoretical perspective, this is a very important question, because then it makes a huge difference between, is this a real phase of matter a new phase of matter, or is just a pre-thermal behavior that at the end of the day is just another type of thermalization dynamics? And this is the big theoretical fundamental question that is missing, I'll say. Okay. So since your correlations they spread so slow, logarithm with time, then it takes exponentially long time to fully reach the saturation, okay? And exponentially with the number of spins that you have in your system. So if you have a macroscopic system, this is more than infinite, I mean close to infinite in some sense. I mean, if you manage to find some analytical form to solve this limit, yeah, that's okay. But I'm not sure if it is going to be some simplification if you look for the large ensemble limit. Okay. So this beta here, it's going to be more related to, yeah, to somehow the effective temperature of your system or to the initial configuration that you put your system. So, you could, you could try to use different betas here and see if your numericals go for. But there is still always the open question that for any beta that you put here, at some point you cannot go for larger systems as well, right? You're going to reach this maximum time limit. The question is going to remain, I think, at the end. Yeah. What I know, I mean, I know actually it's just a few papers that try to address this question, that they are trying to propose some other type of phenomenological models that you put explicitly what will be these thermalizing islands in your localized chain and see the effects of these things there. To see if these small defects or the small thermal defects, they are really able to destroy. And if you have some characteristic trait on how they are destroying the localization. Because then we could look for this other models here to see if there is also these characteristic traits appearing here. Okay. But how they propose the models is, I don't know the specifics.